Hello students, welcome to the new session on Analog Electronics 1. Myself Gunjan Mittal Roy in the Department of Electronics and Communication Engineering in JFET Greater Noida. So we are going to start with our next unit, which is unit 3, and in this we are going to firstly introduce about field effect transistor, its introduction, its classification and its operating point. So we have covered BJT, which is bipolar junction transistor, previously in quite detail with all its biasings, operating conditions, load line, different stabilization circuits, amplifiers, configurations, and so on. So after that, a new transistor, which is field effect transistor, is going to be introduced in this video. Now we should understand what are the basic differences and similarity between the two types of transistors, and on that basis we can conclude that which one is better and which is applicable in which particular condition. That means their advantages, disadvantages and applications that we can conclude in terms of their similarities and differences. So if we talk about the similarities, that both are transistors and they are switching devices, and they are widely used as amplifiers and impedance matching circuits. So these are the applications of both transistors. Firstly, they are amplifiers, they are switching devices, and they are impedance matching circuits. After that, if we talk about the differences of the two, the FET are voltage controlled devices, whereas BJTs are current controlled devices. Like in BJT we have IE equal to IB plus IC. So the collector current is a function of base current, or emitter current is a function of base current and collector current. Therefore, the transistor output current is a function of transistor input current, and therefore it is a current controlled device, whereas the FET is a voltage controlled device, which we will discuss later on in detail in this video. After that, FET has a high input impedance compared to BJT. FETs are less sensitive to temperature variations and are more easily integrated on ICs, and FETs are generally more static sensitive than BJTs. So these all differences we can conclude from these differences. We can conclude that the FETs are much better devices as an amplifiers or switches or matching circuits if we compare with BJTs. So FETs have almost all the advantages compared to BJTs. Now FETs, the classification, if we talk about the classification of FETs, these are classified as junction field effect transistors and MOSFET, metal oxide semiconductor field effect transistors, where MOSFET are of two types, depletion mode and enhancement mode. This is the construction of JFET, that is junction field effect transistor. It has a silicon bar, whether it is N substrate or P substrate, and if it is an N substrate as shown in this diagram, the P type semiconductor is diffused in the opposite terminals, and which are interconnected to each other, and they form gate terminal. And the lower terminal at the bar is called source, and the upper terminal at the bar is called drain. So it also has got three terminals like BJT. These terminals are source, gate, drain. Source is analogous to emitter, gate is analogous to base, and drain is analogous to collector. Okay, so this is the practical example, like source water tap, gate is the control knob, and drain is the output going to the drain. Now operating characteristics. Then if VGS equal to 0, gate voltage is 0, drain voltage increases to positive value. If VGS less than 0, VDS at say some positive value. So therefore it is a voltage control device. That means if we keep the gate voltage 0 or negative or positive, we get different magnitudes of the currents. This we will discuss later on. Now the operating characteristics, when VGS equal to 0, that means no gate bias is applied, only the drain voltage is applied. When VDS increases from 0 to a more positive voltage, that means VDS we are increasing from 0 to a higher values. So when VDS is a positive value, that means drain is positive with respect to source is negative and drain is positive. And this is again the concept that the source should be forward biased and drain should be reverse biased in order to operate it in active region. Because of that, the charges will move from source region and will be collected at the drain region. And along with that, special shape of depletion layer is formed across both PN junctions, which is called wedge shape. It is because the upper PN junction side is reverse biased, as the VDD is reverse voltage for that, and the lower PN junction side is forward biased, as VDD is forward voltage for source terminal. So in forward bias the depletion width decreases, and in reverse bias the depletion width increases. And due to this, peculiar shape which is called wedge shape is obtained in depletion layer, as shown in figure. And if we keep on increasing the reverse bias, and if we apply the gate voltage, which is again a reverse bias, this depletion layer increases. So it is showing the same thing. If VGS equal to 0 and VDS is increased further, if we keep on increasing the voltage between drain and source, and that way only, then the two depletion layers will almost touch each other, and resulting drain current would be 0, and thus this situation is called as the pinch off situation. Okay, this is the VI characteristic curve of JFET. When the voltage is 0, drain voltage applied is 0, there is no drain current. But if we increase it from 0 to a sufficiently high value, the current increases linearly and it reaches a maximum value which is equal to IDSS. And if we at that particular drain current, the voltage is termed as the peak voltage. Now, if voltage is increased further, the drain voltage is increased further, the current does not increase, as we mentioned in previously, that the two depletion layers almost touch each other, and because of this touching, the drain current does not flow further, and we get a saturated value of drain current. It remains saturated. And when VGS becomes more negative, the depletion layer increases. So if now we apply gate voltage also, the gate voltage should also be reverse bias, so the depletion layer increases and the current value decreases, the drain current decreases. So in this way we can say that increase in gate bias reduces the drain current, and therefore it is a voltage controlled device. Now this is the operating characteristic of JFET. It is showing that as the voltage increases, initially the current flows and then it gets saturated at a pinch off voltage, and beyond that, if the voltage is increased further, the current does not increase and it remains saturated. So it is the saturation region for which the current remains constant, and it is the ohmic region near x-axis, near y-axis, where the current increases linearly following Ohm's law. This is the drain resistance, which is given as Rd equal to R naught upon 1 minus VGS upon Vp whole square, where VGS is the gate to source voltage and Vp is the pinch off voltage. Now P-channel JFET can also be operated in the same way, considering the fact that the source should be forward biased by applying positive battery, and drain should be reverse biased by applying negative battery, and also the gate should be reverse biased by applying positive battery. And in the same way we will get the characteristics current. Now the symbolization of N-channel and P-channel JFET. So to symbolize, we use an arrow, and arrow is the direction of from positive to negative. So in N-channel JFET, the P terminal to N terminal we go inside, so the arrow goes inside, and in case of a P channel it is opposite, the arrow is outward. Now the drain transfer characteristic is determined. Out of that we get a drain current, which is given by the Shockley's equation. It is ID equal to IDSS 1 minus VGS upon VP whole square, where IDSS is the drain current at saturation. So this is the Shockley's current equation, quite important to understand, to realize the value of drain current for the given saturation current, gate voltage and pinch-off voltage, or any of these parameters can be determined for given 3 parameters. Then we have a transfer characteristic curve. The transfer characteristic curve means the voltage is the gate voltage and the current is the drain current. So in JFET, if the gate voltage is 0, drain current is maximum, and if the gate voltage is negative, means more the negative gate voltage, higher the negative gate voltage, lower the drain current. So this is the characteristic curve, which is showing that increment in gate voltage, which is a negative voltage in case of a N channel JFET, to make it reverse bias, the current decreases. So it is the transfer characteristic. Thank you so much.